Right. Next, we'll move on to Dimitri Veras, who I think will tell us about some of the theory of how these planets around white dwarfs form and evolve. Okay, Dimitri.
Okay, Jim, can you hear me and see my screen?
Yep, looking good.
Okay, well, thanks a lot. And I'll pick up from where Boris left off, but first I'd like to thank all of the organizers of the Exostar program for bringing together a group of people with whom I was able to form new collaborations with and also perform several different studies both on giant star and white dwarf evolution. I talked about my collaboration with Tiago Campante yesterday about astroseismology with red giant stars, but today I'm going to focus on planetary systems around white dwarfs, and particularly the theoretical aspects of them, as Boris covered the observational aspects. Going into the program, I had the intention of investigating tidal interactions between giant planets and white dwarfs, because prior to 2019, that hasn't really been done in a dedicated study. And Jim Fuller was a great collaborator for that purpose. And then by chance, Alex Volshin was sitting in the office right next to mine, and we were both thinking actually about radio-loud planetary cores orbiting white dwarfs. And that eventually turned into a good collaboration and a paper that is effectively a follow-on from what Boris talked about. And also during the original Exostar conference, J.J. Hermes gave a talk about how to potentially constrain the host star masses of main sequence stars based on constraints we have for planets orbiting white dwarfs. And that idea stuck in my mind for a while. It took a long time, but eventually we instantiated that into a paper. And ironically, JJ was an office mate of mine for 2 years, but we never actually published anything together. So it actually took the Exostar conference for us to finally make that connection. But the paper that Jim and I, the first paper that Jim and I wrote was a general paper modeling this tidal interaction between giant planets and white dwarfs. And we made it general, figuring that in the future, just as Boris mentioned, there would be more planets like the evaporating planet that he found that would be discovered. So it could be applied to a variety of different planetary systems. But then after Boris's paper was published, we were able to apply this formalism specifically to this one system, which I'll call 914. And so to go into the theory behind these papers, it's effectively how do we circularize and shrink a highly eccentric expanded orbit in a very short period of time. And to do so, we invoke chaotic tides. And the pioneers of chaotic tides are listed there in the citations which you actually see. And what do I mean by a chaotic tides? And I mean the stochastic orbital evolution that occurs when F modes are excited within the planet during every pericenter passage. During each one of these passages, there's an exchange of energy between the modes and the orbital angular momentum. And it's only active for highly eccentric orbits. And the result is illustrated on this screen here, where you can see the semi-major axis versus time and the eccentricity versus time for a few different Jupiter-sized objects. Now, the parameter U here refers to how close the pericenter is to the tidal disruption radius. So if U is less than 1, then the planet gets disrupted. And the takeaway here is that the semi-major axis of a scattered planet that reaches very close to the star, the white dwarf at orbital pericenter, it can shrink its orbit, its semi-major axis, by over 95% in just a few million years' time. The eccentricity actually doesn't change very much, so it still remains highly eccentric in that time, but the semi-major axis is shrunk. Now these curves here, they stop when the chaotic tidal evolution ends. And at that point, one can invoke a more traditional, a standard equilibrium tidal friction approximation to circularize that eccentricity from 0.95 down to whatever value we actually think the planet currently has. Now, that additional computation is dependent on the modified planetary quality factor. And so given the cooling age of the white dwarf, or how long the star has been a white dwarf, then that actually constrains the range of potential Q values. Now, there's an interesting twist to this story, and that is that during every pericenter passage, the mode energy actually builds up in the planet, and that can become a significant fraction of the binding energy. So that actually, during chaotic evolution, depending on the planetary structure, several thermalization events can occur. Now, what happens to the energy during these thermalization events is not necessarily clear. I think that Michelle Vick is actually doing some physical modeling about where this energy goes, and I'm quite excited to see her results. But if the energy becomes about 10% of the binding energy, then it only takes 10 of these thermalization events to potentially actually unbind the planet. And so if you make this assumption, saying the planet's actually destroyed after a certain number of these thermalization events, then you could look towards what types of planetary structure could that occur for. And it turns out that the more inflated a planet is, the more likely that they are to experience these thermalization events during chaotic tidal evolution. As you see here, an ice giant is more easily thermalized than a heavy gas giant. So that's the general theory. Now, what about the specific 914 system? Well, in this system, you first have to scatter the planet very close to this white dwarf. And to do that, we can use other planets, which should be about the same size or larger, as you see in this diagram here, where a planetary system can remain stable throughout the main sequence, stable throughout the giant branch phase, and stable for a certain period of time during the white dwarf phase, and then scatter off one another, where the innermost planet here comes very close to the white dwarf. Now, another possibility is that the scattering occurs due to a binary stellar companion. And Alexander Stefan is currently writing a paper that explores that possibility for this system. And then after that planet gets scattered towards the white dwarf, it'll eventually circularize as I've described. Now, for this particular 914 system, we were able to constrain the types of planetary structures which are most likely to generate this chaotic tidal evolution. So here's a plot of semi-major axis versus orbital pericenter, and everything to the left of the solid lines allows for chaotic tidal evolution to occur. Everything to the right does not. So we need to be to the left of these solid lines. And given the likely orbit of this planet, we also need to be in the green shaded region, because during the pericenter evolution, the pericenter probably changed from about 0.035 AU to 0.07 AU. And the only planetary structure which fits these criteria is what's known as a superpuff structure, so a very inflated structure. And that's what we assume that this planet is, if it currently is actually on a circular orbit at 0.07 AU. Now, as for follow-ups to the study, I'm aware of 3. There certainly might be more. One of these follow-ups is to explore why there are actually no rocky pollutants in the atmosphere itself. And it turns out that the planet can act as an effective barricade when rocky boulders are radiatively dragged towards the planet. Now, there's another study that actually explores the stability regions of the gas disk, which potentially could be important for future observations. And finally, as I mentioned, Alexander Stefan is considering a binary scattering scenario. So in the last few minutes, I just want to talk about this collaboration with Alex Volshin, and Boris showed the same figure. Just to describe this more, what we were thinking about was if you have a magnetic white dwarf and you have a conducting core of a planet, then a unipolar conductor circuit could be formed, just like in Jupiter, just like the Jupiter Io system, whereas here the white dwarf is Jupiter and the planetary core is Io. Now, this can generate a Lorentz drift, which drifts the planet towards the white dwarf. Now, also, there is a gravitational tidal interaction between the white dwarf and the planet. And the previous studies have only considered the Lorentz drift. So what's new about our study is that we couple the Lorentz drift with the gravitational tidal interaction between the white dwarf and the core. And these are not really separable equations. They are linked. And so what we computed are the lifetimes of the planets before they get engulfed in the white dwarf. And so that's what this sort of pictogram shows. Each number here represents the number of roughly the number of years that the planetary core survives. So a 0 is 10 to the 0 years, a 7 is 10 to the 7 years, and the red colors refer to the fact that in 1 year, those cores will be destroyed. And over a wide region of parameter space, we do find survival for appreciable timescales. And this has prompted observational campaigns on Arecibo and GBT. Now, the x-axis here covers the range of magnetic field strengths that we could expect, 10 to the 3 to 10 to the 9 Gauss, and the y-axis here covers the different magnitudes of electrical conductivity in the atmosphere. And then each row corresponds to a different distance away from the white dwarf. So we do find that survival is certainly possible. And also, we derived our equations assuming a fairly simple prescription for Lorentz drift. Now, Dong Lai in 2012, he actually considered what happens if the magnetic flux tubes twist during this evolution. And he found overall that these survival lifetimes could be longer. He didn't incorporate gravitational tides in his study, so it's not so easy to compare them. But overall, I think this enhances the possibility that we might be able to observe these cores around white dwarfs. And with that, I will conclude and take any questions. Thank you.
All right, thank you, Dimitri. We have questions for Dimitri? So I have one about the tidal interaction, Dimitri. How does that actually affect things? Because so presumably you'd keep the planet tidally synchronized as its orbit decays, and that would just make the orbit decay a little bit faster. But I wouldn't guess it has a big effect. Is that true?
So it actually, that's the link is with the spins of the planet and the star. And depending on the parameter space, we found that in most regions of the parameter space, they could be decoupled, but there is a small region where it's not necessarily true. And the gravitational tidal prescription that we use is one based on Fourier expansions of the tidal quality factor. So there are quite a few. This is based on much of the work from Efroimsky and Makarov. And so there are quite a few parameters in those studies. So the parameter space is quite significant. And there is a region of that parameter space where the coupling does become important.
Okay, but mainly it just affects the spin, not the orbit so much. Okay. Okay, other questions for Dimitri? We have one raised hand from Lauren. Lauren, yeah, I believe you can talk. Yeah, go ahead.
Yeah, hi, Dimitri. Great talk. Thank you for that. This is really exciting. I hadn't, I guess, heard about your work on this chaotic F mode excitation. And I'm curious, could it happen for main sequence stars and affect planetary evolution there, or is it really limited to these compact white dwarfs?
Well, thanks a lot, Lauren. So in fact, most of the initial work on this chaotic tidal evolution, like in the references that you see here, that has been geared towards main sequence stars. And so in fact, it is one way of actually producing hot Jupiters on short timescales. The real difference with main sequence stars is the stellar ages are not as well constrained as the ages that we have for these white dwarfs. Like for this particular 914 white dwarf, the age is 13.3 plus or minus 0.5 million years. which is extraordinary. So therefore, it does call on the theory to be a little bit more detailed when we have such good constraints. But certainly, it has been applied around main sequence stars.
Okay, great. We also have a question from Jamie Tyar. Can the chaotic disruption happen at the same time or same distance or say for the same planets as the magnetic unipolar induction?
Well, that's an interesting question. I haven't thought of coupling the two studies in that way, because for the planet that Boris published on, that white dwarf is not known to be magnetic, and so I don't know, but potentially if there was a planet that or a core that was discovered around a magnetic white dwarf, then that would be an important consideration. Yeah, thanks for the question, Jamie.
Yeah, I think in principle they could happen at the same time. I guess this is pretty unlikely because the chaotic tides, that phase of evolution is usually very brief, right? Like less than 1 million years.
Yeah, it's really a scale issue.
Mm-hmm.
Yeah, I think so.
But yeah, might be possible. Then it would be pulsed unipolar emission too, only at periastron, so that would be quite strange.
Okay.
Okay, well, I think we've used up our allotted time for the talks, so now we can move into the more general discussion.